In the previous differential equation video, we introduced the notion of homogeneous equations and we saw two examples. Today we are going to solve those examples. And this is the first one. Here the equation is x square minus 3y square dx plus 2xy dy equal to 0. And in solving this, we are going to take the help of that theorem that we saw in the previous video, which tells us about a transformation. That the variables x and y that you see here, we are going to introduce a new one v such that y is equal to vx. So let's see how the solution goes. Accordingly, we start the solution by mentioning that fact. We have already seen that the given equation is homogeneous, and in fact it can be expressed in this form: dy dx equals minus x divided by 2y plus 3y divided by 2x. That is, when you express the differential equation in derivative form, then the right hand side becomes a function of x divided by y only, or y divided by x. Anyway you can view at it. So now here we are going to apply that transformation, y equal to vx, which will turn this equation into one having only the variables v and x, and that equation will be a separable equation, and then we can solve that. So this is the transformation, y equal to vx. V is our new variable. Now treating v as a differentiable function or differentiable variable of x, we differentiate both sides with respect to x. That gives us dy dx plus, here of course in order to differentiate the right hand side you have to apply the product rule for differentiation. So if you keep v as it is and differentiate x, you get 1. So that way you get v here plus x times dv dx. Now we are going to use this here, and here also there will be change. Changes means in place of x divided by y, you can write 1 divided by v, and in place of y divided by x you can write v. So after this transformation, the above equation becomes, above equation means this equation. If you want to be more clear here, you better give this some number and refer to the equation using that number. So anyway, it becomes what? In place of dy dx, we have v plus x dv dx, and this one becomes minus 1 divided by 2v plus 3 divided by 2v, that is 3v divided by 2. And then after some algebraic manipulation, you can see that you can separate the variables v and x like this. I haven't shown the intermediate steps because that's just simple algebra. So now you can of course integrate both sides and get your solution. Now integration is very easy. The differential of the denominator here on the left hand side, that is d of v squared minus 1, is to v dv. So the integral of the left hand side is the natural logarithm of mod v squared minus 1. Similarly, this is even more direct. It's just ln of mod x plus ln of mod c, where c is an arbitrary constant. Now we just have to simplify things and we have to write what v actually is, y divided by x, so that things can be brought back in terms of y and x. So you do understand what will happen to this right hand side. It will be natural logarithm of mod x times mod c, which becomes modulus of cx, absolute value of cx. And then after cancelling logarithm from both sides, this is what you have. Where now if you use the fact that v is y divided by x, it becomes this. And you can multiply both sides by x square, because your x is non-zero. You see, whenever we are dividing by anything, we are assuming that it's non-zero. Okay, so we do not mention those assumptions explicitly. That does not mean that they are not there. They are always there. X here is non-zero, so x square is positive, and that is why if you multiply both sides by x square, this is what you get as your final solution. But of course, if you put additional restrictions on x and y, then this can be simplified a little more. like this next one, like this one. If y is greater than or equal to x and they are both non-negative, then y square minus x square is non-negative, so the left hand side will be this, and because x is non-negative and with the understanding that c is an arbitrary constant, so you can just simply take c to also be non-negative and have cx here, so that way you will get cx cube. But in general, this is the family of one parameter family of solutions. To what? To that equation, that separable equation. Whether this is also a one parameter family of the original equation, that remains to be seen. Here, however, we are not concerned about those things. We just want to see how the method works. That's our aim for now. Later, when we go to more advanced parts, there we will be concerned with whether what we are finding really are the solutions to the original equation. Right now, however, we suspend those endeavors. Next, we have example 13. Here, instead of simply a differential equation, we have an initial value problem, where the equation is actually that one, that other example that we saw in the previous video. Y plus square root of x square plus y square dx minus x dy equal to 0. And this one also we saw back there that it's a homogeneous equation. And additionally, you have this initial condition also. At the point x equal to 1, the solution y should have the value 0. So here also the solution starts by recalling that we already know that the given differential equation is homogeneous. And it can be expressed in the derivative form like this: dy dx equals y plus square root of x square plus y square divided by x. Now, it is given that the initial value is 1. So, we can assume that x is greater than 0. What does it mean? It means that the differential equation is defined on an interval that lies to the right side of 0. So that is why for us, not just this value, but any x value that we choose will be from that interval. Which interval we don't know, but it is some interval on this side of 0. And what does that allow us to do? That allows us to write x as this, square root of x square. In general, for any real number x, this is equal to the absolute value of x. But x is positive, so that becomes x. So that means if you write this in place of this, then x square goes inside the square root, and so the inside becomes this 1 plus the square of y divided by x, and outside of course we have y divided by x. In fact, we noted this when verifying that this is a homogeneous equation in the previous video. So now we just have to simply again apply that transformation y equal to vx, turn this into a separable equation and then solve it. So we write the transformation y equal to vx, and again dy dx is v plus x dv dx, and then we use that here. V plus x dv dx equals, what will happen to this? Y divided by x is v. So the right hand side becomes v plus square root of 1 plus v square. And now of course this will be simplified. Already you can see that you can cancel v from both sides. So after some simplification, this is how the equation looks. dv divided by root 1 plus v square is equal to dx divided by x. And now we can integrate both sides. So if you do the integration, do not forget that the denominator here is not merely 1 plus v square, but square root of 1 plus v square. So from table of integration, this is the integral. ln of absolute value of v plus root 1 plus v square. And the right hand side is as before, ln of mod x plus ln of mod c, where c is an arbitrary constant. So after this is what you get. I mean, you know what to do. The right hand side will become ln of mod cx, and then you can cancel ln from both sides, But what happens to the modulus? Why are we able to lift the absolute value just like that? See, ideally when you lift absolute value from an equation where on both sides you have absolute value, you should ideally write plus or minus, but because we have an arbitrary constant c here, so that plus minus gets absorbed by c itself. So that's how this is what we get. And here again you write in place of v y divided by x. So it becomes this, and then after further manipulation, this is how your one parameter family of solutions looks. Y plus square root of x square plus y square is equal to cx square. And now from here, we have to find the value of c using that initial condition, that at the point x equal to 1, y is 0. What will you get if you put y equal to 0 and x equal to 1 here? Y is 0 and x is 1, so the left hand side becomes 1 and the right hand side becomes c because x is 1. So that's how you get c equal to 1 because of this initial condition. And that is why the particular solution which comes from that initial condition is this equal to x square. And if you do some further calculation here, then you can write y as a function of x, an explicit function of x. The intermediate steps I am leaving to you. You do understand what you have to do here, right? You take y to that other side, x square minus y it becomes, and then you square both sides, and then you will realize how this one comes. So this is your particular solution or the solution to the IVP. And this is where this section ends. After this we have exercises and we will solve a few of them to see how things go. I mean the things that we learned here, how we can use them to solve the exercises. And then in the next section we have linear equations and Bernoulli equation. So see you in the next video on differential equations with those things. Until then, this is me, Lucifer from A Mathematical Group. Have a nice day.